Well, right, welcome back. And in this lesson, we are going to look at calculations that involve the Raoult's law. In our previous video, or in our previous lesson, we looked at the connection that leads to the formulas that we shall be using to calculate. And we looked at ideal solutions, their properties, we looked at Raoult's law and its connection to Dalton's law. So in this video, we are going to look at how to apply all the knowledge from lesson 4 to calculate here. This is our lesson 5. Don't forget to subscribe. So a mixture of benzene and methylbenzene forms an ideal solution. It is true because these ones, it means that they obey Raoult's law. Number 2, the forces of attraction between their like molecules and unlike molecules are equal in magnitude. So when they say calculate the vapor pressure of the solution, calculate the vapor pressure of the solution, it means they need the total vapor pressure. But we say that we need first to get individual partial vapor pressure. After getting the individual partial vapor pressures, then we shall sum them up. But to get individual partial vapor pressure, we need the mole fraction of each. Then we multiply the vapor pressure at a particular temperature. So we need to first look for the formula mass because we are given masses, meaning given masses, we can find the number of moles. And when you're given masses and you need the number of moles, you need to first calculate the relative molecular mass. So our part A, let's look for the formula mass of benzene. Formula mass of benzene is going to be equaling to 12 times 6 plus 1 times 6. And the formula mass is 78 grams. Then formula mass of methylbenzene is C7H8, and it's going to be 12 times 7 plus 1 times 8 is 84 plus 8, which is 92 grams. So we can easily get the number of moles of benzene. So moles of benzene are equal to the mass of benzene, 1.95, divided by its formula mass, which is 78. So this one will give us the moles of benzene as 0.025. Then we also go ahead to look for the moles of methylbenzene. It's going to be equal to the mass of methylbenzene, 4.6 over the over the molecular mass, which is 92, and this one is going to give us 0.05 moles. So after getting the moles, we need the mole fraction. But to get mole fractions, we need the total moles in the mixture. Total moles in the mixture are going to be equal to 0.025 plus 0.05. So the moles will be 0.075 moles. So the mixture has got 0.075 moles. So after getting the total number of moles, all right, we can get the mole fraction of each. Mole fraction is you get the number of moles of that component, you divide by the total moles of that component. So it means that the mole fraction of benzene is going to be equal to the moles of benzene 0.025 out of the total moles, 0.075. Then the mole fractions of methylbenzene is going to be equal to moles of methylbenzene. Those are 0.05 over the total moles, 0.075. Now, since we have the mole fractions and we have the vapor pressure of pure components, we cannot fail to get the vapor pressure of our solution. So let's move with this. And we first get the partial vapor pressure of benzene, partial vapor pressure of methylbenzene, then we get the total. So partial vapor pressure of benzene is going to be equal to mole fraction of benzene times its vapor pressure in its pure state. So it is going to be 0.025 out of total 0.075, that is the mole fraction, times its partial pressure. This one will give us the partial pressure of benzene. Then partial pressure of methylbenzene is going to be equal to, let me call it M. Methylbenzene is going to be equal to mole fraction of methylbenzene times partial pressure of methylbenzene in its pure state. Mole fraction of methylbenzene is 0.05 out of total 0.075 times its partial pressure 8.2. This one will give you the partial pressure of each component. So let me calculate each by putting on my calculator here 0.025 times 10 divided by 0.075. This one will give you 3.33 kilopascals. Then for this, we are having 0.05 times 8.2. We divide by 0.075. So this is going to give you 5.467. But they need the calculate the vapor pressure of a solution. So we need P total. It's going to be equal to partial pressure of benzene plus partial vapor pressure of methyl benzene, which is going to be 3.333 plus 5.467. So plus 5.467, which is going to give us 8.8 kilopascals. So that is our part A. Then part B, they want us to calculate to determine the composition of vapor of the above solution. Let's begin with benzene, composition of benzene in vapor. We say that this is equal to mole fraction of benzene times its partial vapor pressure in its pure state out of the total vapor pressure. Composition of the vapor. So we talk about each one separately. So mole fraction of benzene times partial pressure, it gave us 3.333 out of P total, which is 8.8. So the XB, composition of benzene in vapor, is equal to, when we work out this, which is 0.378. Right? Now, for methylbenzene, XM, composition of methylbenzene in vapor, also is equal to mole fraction of methylbenzene times partial pressure of methylbenzene at pure CDN over P total. The upper one is 5.467 divided by P total, which is 8.8. And this is going to give us 0.622. Alternatively, for the second component, after getting the first component, alternatively, for the second component after getting the one of benzene, we would have said that for methylbenzene in vapor is going to be 1 minus the one of benzene in vapor. Since we said that the mole fractions, once summed up, they give us a 1. So still you will get the same answer as that. Right. Let me do question 2. Methanol and ethanol form an ideal solution. Methanol and ethanol form an ideal solution. A, calculate the vapor pressure of a solution containing 2 moles of ethanol, of methanol, and 1 mole of ethanol at 335 kelvins, brackets vapor pressure of methanol and ethanol are 8.1 times 10 to the power 4 pascals and 4.5 times 10 to the power 4 pascals respectively at 335 kelvins. B, calculate the composition of vapor formed from the mixture. In A, above. Then C, which of the 2 liquids is more volatile? Give a reason for your answer. Have to give a reason for your answer. So is our question, and let's work out the solution for this. Methanol and ethanol form an ideal solution. Yes, meaning that the moment they say form an ideal solution, the aspect of Raoult's law should start clicking there and then. Now, for part A, allow me let E represent my ethanol and M represent methanol. Now they want me to calculate the vapor pressure of a solution. But remember, the vapor pressure of a solution is the same as P total, which is equals to partial vapor pressure of methanol plus partial vapor pressure of ethanol. Now, partial vapor pressure of methanol is equal to mole fraction of methanol times partial pressure or vapor pressure of methanol in its pure state. Mole fraction, they gave us moles of methanol and moles of ethanol. So the total moles are 3. 2 moles of methanol, 1 mole of ethanol. Total moles 3, meaning if I need the mole fraction of methanol, it's going to be 2 out of total 3, then times the partial, the vapor pressure of methanol in its pure state, which is 8.1 times 10 to the power 4. So this one will give me the partial pressure of methanol as 5.4 times 10 to the power 4. Then I also look for the partial pressure of ethanol, which is equal to mole fraction of ethanol times vapor pressure of ethanol in its pure state. So mole fraction of ethanol is, the moles of ethanol is 1 out of the total 3 times its vapor pressure in its pure state, that is 4.5 times 10 to the power 4. So the partial pressure of ethanol is going to be 1.5 times 10 to the power 4. Then this one will imply that my P total is going to be equal to 5.4 times 10 to the power 4 plus 1.5 times 10 to the power 4. And this is going to give me 6.9 times 10 to the power 4. The units are pascals. So that is the total pressure. Now they are saying which of the two liquids is more volatile? No. Before that, part B, calculate the composition of vapor. Calculate the composition of vapor. Now, let's begin with the composition of methanol. Composition of methanol in vapor would be equaling to mole fraction of methanol times its partial pressure or times its vapor pressure in its pure state out of P total, which is going to be mole fraction of methanol. The whole of this, the numerator is already calculated here, which is 5.4 times 10 to the power 4. We shall divide it by the P total, which is 6.9 times 10 goes to the power 4 to the power 4. So this mole fraction or the composition in vapor is going to be 0.783. After getting this, then we can also get for ethanol in vapor. And this is going to be 1. We say that it's the same as 1 minus 0.783. So it is going to give you 0.217. As simple as that. Then part C, which of the two liquids is more volatile? It is methanol. You're going to conclude that methanol is more volatile because it has a higher composition in the vapor phase. We deduce the volatility of a component by calculating its composition in vapor. The one with the higher composition, this has 0.783, this has 0.217. So, but the one with a higher composition in vapor is the one that is more volatile, meaning that the boiling point of methanol is lower than the one of ethanol because it goes into the vapor phase very easily, meaning it requires low temperatures to go to vapor phase. Additionally, its composition is a reducing factor. Its composition is a reducing factor to as why it is more volatile, or volatility, the ability to escape into the vapor phase. Since its composition is high in vapor phase, then it is highly volatile. As simple as that. I normally believe in doing very many examples. And here I come with another example. Here I come with another example. And this is example 3. The circulated vapor pressure of benzene and toluene are 957 millimeters of mercury and 378 millimeters of mercury respectively. Calculate the composition of toluene, of benzene toluene mixture at 760 millimeters of mercury. B, calculate the composition of benzene in vapor phase. C, state which one of the two liquids is more volatile. Give a reason. Here, they gave us the saturated vapor pressures of benzene and toluene. When we say toluene, that is methyl benzene. This is 957 and this is 378 respectively. They want us to calculate the composition of benzene toluene mixture. They have not given us moles. They have not given us anything to do with the moles. They have just given us the saturated vapor pressures. Okay. Now, this question seems to be harder, but it is the easiest. Let's let benzene, let my B represent benzene and let T represent toluene. Now, it means that P total is equals to, P total is equals to partial pressure of benzene plus partial pressure of toluene. And this is the same as, to get partial pressure of benzene, that is mole fraction of benzene times vapor pressure of benzene in its pure state plus mole fraction of toluene times its vapor pressure. So we have that. But you need to know that mole fraction of benzene plus mole fraction of toluene should be equal to 1, meaning that mole fraction of benzene is the same as 1 minus mole fraction of toluene. Then now I can substitute in P total. They've told us to calculate the composition of benzene toluene mixture at 760 millimeters of mercury, meaning the total pressure is 760 millimeters of mercury, which is equals to, I substitute here, partial pressure. This toluene, we've gotten XB as 1 minus XT. Okay, so it will be 957 partial pressure of benzene, 957, then times XB, which is 1 minus XT. So it will be 957 into XB, which XB is 1 minus XT. Then plus XT, H is a subscript, xt is a subscript, the T is a subscript, which is simply xt. Then times its vapor pressure, which is 378. Now, this one will give us 760 is equals, I'm attempting part A, is equals to, open brackets, 957 minus 957 xt plus 378 xt. So here, we are going to bring this on this side, 760 minus 957, you will get negative 197 is equals to minus 957 plus 378, you're going to get minus 579 xt, meaning that the mole fraction of toluene is equals to 0.34. This we've gotten the mole fraction of toluene, then we can also get the mole fraction of benzene, which is 1 minus 0.34, and it is going to be equal to 0.66. Now, that is it. Capture the composition of benzene toluene mixture. So the composition of toluene is 0.34, while composition of benzene is 0.66. As simple as that. Then B, capture the composition of benzene in vapor phase. Composition of benzene in vapor phase is equal to mole fraction of benzene times vapor pressure of benzene in its pure state out of P total. Mole fraction of benzene is 0.66 times vapor pressure of benzene in its pure state, that is 957 out of P total, which is 760. And this is going to give you 0.83 in vapor phase. State which one of the two liquids is more volatile. Of course, even if you look for the composition of toluene, by getting 1 minus this, it can't be greater than this. So it means that benzene is more volatile because it has a higher vapor composition. So benzene is more volatile because it has a higher vapor composition. This question here, I don't want you to be too much confused. They gave you the saturated vapor pressures only. They have not given you any moles, but they want you to calculate the composition, calculate the mole fraction. Mole fraction is the same as the composition. So that is how best we could do it. Let me do you the last question, then I give exercise to be attempted by each viewer. Number 4. The vapor pressure of ethanol at 20 degrees Celsius is 43.6 millimeters of mercury, while that of benzene at the same temperature is 75.2 millimeters of mercury. The mole fraction of benzene is 0.09 for a mixture of benzene and ethanol at 20 degrees Celsius. Calculate Calculate the Roman 1 vapor pressure of the mixture. Roman 2 mole fraction of benzene in vapor phase. Solution. Roman 1. They gave us the vapor pressures of ethanol and the one of benzene, right? They went ahead to give us the mole fraction of benzene. So if you have mole fraction of benzene, you can easily get that of ethanol. So let's first look for the mole fraction of ethanol. And it will be the total, which is 1 minus the one given, 0.09. And this is the same as 0.91. But they need vapor pressure of the mixture. So they need total is equal to pressure of ethanol plus partial pressure of benzene. But for ethanol, it is mole fraction of ethanol times vapor pressure of ethanol in its pure state plus partial pressure, the mole fraction of benzene times its partial pressure of vapor pressure of benzene in its pure state. Now, mole fraction of ethanol is 0.91 times its vapor pressure for ethanol. We have 43.6. But mole fraction, of course, the total is 1, so it is 0.91 over 1, over 1. It will give you that. Then plus, for benzene, the mole fraction is 0.09 over total, which is 1, times its vapor pressure, which is 75.2. And this is going to give you 39.676 plus this one here, 0.09 times 75.2 is going to give you 6.768. So this one is going to give you the total as 46.444 millimeters of mercury. Interesting. Then in Roman 2, they want us to find the mole fraction of benzene in vapor phase. So they need mole fraction of benzene in vapor phase. It is going to be equaling to mole fraction of benzene times its vapor pressure in its pure state out of P total. So it's going to be mole fraction of benzene times its vapor pressure. It is the whole of this, which we got as 6.768 divided by total, which is 46.444. So when you convert this, or when you work out this on the calculator, it's going to give you 0.146. So that is the answer. Now, I'm going to give exercise, which will be done by all viewers, And well, this is going to serve as an assessment tool to see if few people really have understood this. Exercise 1, the vapor pressures of methanol and water are 125.9 millimeters of mercury and 23.8 millimeters of mercury, respectively, at 20 degrees Celsius. Calculate Roman 1, vapor pressure of a mixture containing 21.0 grams of methanol and 89.0 grams of water at 20 degrees Celsius, and we are assuming that the two liquids form an ideal solution. That is 1, 2. Two pure liquids, A and B, have vapor pressure of 1.5 times 10 to the power 4 pascals and 3.5 times 10 to the power 4 pascals, respectively, at 20 degrees Celsius. If a mixture of A and B obeys Raoult's law, calculate 1, composition of liquid mixture of A and B, which has a total vapor pressure of 2.9 times 10 to the power 4, 2.9 times 10 to the power 4 pascals at 20 degrees Celsius. Roman 2, calculate also the composition of the vapor. That is part A. Part B of that question, state which of the two liquids A and B is more volatile. It's more volatile. Here on number 1, it was supposed to have 2 parts. The second part is to calculate the composition of the vapor, composition of the vapor above the mixture. Composition of the vapor above the mixture. You have to know that when they say composition of the vapor above the mixture, you look for each composition of methanol in vapor, composition of water in vapor. So that is it for this lesson. I wish you all the best. Next time we shall be looking at the phase diagrams of ideal solutions. I wish you all the best. Till we meet again. Thank you.